All right, let's do a little review for the test coming up. One of the first things we talked about were atoms. Atoms have the same number of protons as they do electrons, positive protons, negative electrons. Then we talked about ions, and ions were ones that were charged, whether they were positive or negative. How did they become charged? Well, if you lose an electron, let's say you lost that electron. If you lose an electron, you then become positive, okay? If you gain an electron, now you have, let's say, 22 electrons versus 21 originally, or 21 positive protons, 22 negative electrons. Now you have an extra negative charge, so whatever would gain that electron becomes negative, okay? So losing electrons, losing means you're going to become positive. If you are gaining that electron, you'd be then negative. Now, if you do lose an electron and you become positive, what's that positive ion called? It's called a cation. Okay? Cations are positive, and then this negative ion is called anion. Okay? So you got cations and you have anions. We also talked about Lewis dot structures. In a Lewis dot structure, one of the ones that we did a lot was carbon's Lewis dot structure. And when we drew on those dots, what do those dots represent? These dots are valence electrons, okay? Valence electrons. Now, why were valence electrons important? They're the ones way out in the outermost energy level. If you saw any sort of electron shells that kind of look like this, that outer shell is always called your valence shell. So there'd be one valence electron there. Or if you see two in that outer shell, then there's two valence electrons, okay? They're the ones involved in the bonding process. So we got your cations, your anions. We see these dots, these Lewis dot structures. Those are your valence electrons. Something else that we talked about were those oxidation numbers. So kind of going off of this, I think I got the red on red here. All right, so oxidation numbers. Let's say we did lose that one valence electron. This oxidation would be +1. If you lost 2 of those electrons, now we are +2. Okay, and then on the other hand, if you've gained 1 electron, you're -1. If you gain 2 electrons, you're -2. Those are our oxidation numbers, or our charges. And then once we knew what the charges were, we were able to figure out what type of cations, typically metals, bonded with what type of anions, typically your nonmetals. So it's kind of cool to see which ones we could pair together and if they work together nicely. If you had a cation that was +1, like sodium per se, sodium is +1, then you had an anion which is -1, we could go with chlorine. Chlorine has a charge of -1. Well, sodium was +1, chlorine's -1, so when those two go together, you could simply just write the formula as NaCl because those charges cancel out and it goes together nicely. And that was kind of the whole component of how do we form these chemical formulas. Well, you first have to figure out what the charge of each of those ions are and see if they go together nicely. If they do, then you don't need any numbers. And if you do need some of those numbers, remember that we call those little numbers subscripts. But if you do need a number, that would be like if you were trying to bond sodium with something with a -2 charge, like oxygen. Oxygen is -2. So if you're trying to do sodium, which is +1, with oxygen that's -2, you would need Na2O. You would need 2 of those sodiums to cancel out that -2 charge on oxygen. Okay? And that's how our oxidations worked. And kind of the whole thing that started that was that electron moving over, or the electron kind of, you could say, transferring. Whenever you see the word transfer, that is dealing with an ionic compound, okay? Ionic compounds deal with a transfer of that electron. So one becomes positive, one becomes negative, opposites attract. The other type of bond we had was a covalent bond. Now, covalent bonds, we're not transferring those electrons. Covalent bonds were when we were drawing those Lewis dot diagrams and connecting the dots. We weren't transferring the electrons, we were sharing them. Sharing is covalent, sharing is caring. Covalent dealt with sharing of electrons. Ionic was transferred. Okay? Some other things we talked about was electronegativity. I talked a little bit about the grade point average, or a 4.0 is kind of the best grade point average you can have. A 4.0 electronegativity means it's a very strong atom. And one of the strongest ones was chlorine on there, so that means if chlorine is going to bond with something like sodium, or chlorine is so strong that that electron basically gets transferred or pulled all the way to chlorine, and hence the word transfer in an ionic bond. So electronegativity just deals with how strong or how much those electrons are going to be attracted to that certain atom. Another thing we talked about were just type 1 compounds, which when we're naming type 1 compounds, we're always going to be a metal plus a non-metal. Okay, so type 1 was a metal plus a non-metal. When we were naming these, all you have to do is say the name of the metal, like sodium, and then the non-metal, the last 3 letters would end in IDE. So if you had a metal like sodium bonding to chlorine, we would call this sodium chloride. Okay, so NaCl would be sodium chloride, and that's a type 1 compound. A metal, which we know the charge of, so it's going to be from group 1, group 2, possibly group 13, like aluminum over there. So these are type 1 compounds. Type 2, okay, type 2 is still a metal plus a non-metal, but the metal is unique. It is a transition metal. All right, transition metal plus non-metal. So with type 2, instead of something like sodium bonding with chlorine, we would have something like iron bonding with chlorine. So iron would be our transition metal, chlorines are non-metal. And then the rules here when you name it is you have to use Roman numerals. So how do you do that? Well, you first have to figure out what the charge of chlorine is. Chlorine is a -1 charge. So if I were to put this formula together with no numbers and I just wanted to write FeCl, well, that would tell me that this charge on iron here must be +1, because we know chlorine's -1. So iron has to be +1 here, so when you name it, we would say iron 1 chloride. Iron 1 chloride, hopefully you can see that there. But iron 1 chloride indicating 1 as the charge of iron there. Next, type 3 in our final type. Okay, so type 3, you're not going to have any metals in the formula whatsoever. You're going to have non-metal here plus non-metal. So a couple non-metals, you could have carbon plus oxygen. Let's say, and then with type 3, the charges don't necessarily matter in this case. You're just really looking for carbon here and how many oxygens. If we have just 1 carbon and 1 oxygen, it would form CO, which we would call carbon monoxide. And the prefix mono is because there's only 1 carbon there. 1 oxygen there. Now, if we had something like carbon plus 2 oxygens forming CO2, that is called carbon dioxide. And di is the prefix for 2. Okay, so carbon dioxide there. And you guys can, I would highly suggest you write those Greek prefixes on your note card, so that way you don't have to memorize them, but some of you probably have the hang of them by now. So those are our 3 types. One other thing that you might see on the test would be your polyatomic ions. So just remember, anytime you have a polyatomic ion, you leave the name as it is on that chart, and you'll have that chart on the test as well. But that should cover a majority of the things that you're going to see on the test. Please come to me if you have any other questions, but